cluster at Columbia, including PI, and we'll be in Waterloo for a lot of the semester. We'll see them again here full time. We do the semester. Kristen worked on a bunch of different things, has worked on them in a bunch of different places. Apart from this kind of stuff, he also has a bunch of interests in astrophysical fluid dynamics, particularly as they relate to planets. And yeah, you can tell us about Spacetime Sirens.
Thank you, Matt. Thanks for the invitation to talk about this. So first let me mention that much of what I'm going to show you is really has to be taken as toy models for these sources. And my talk is just an advertising to try to get people interested in this. I think there is a need for more modeling, or at least I think more modeling would be interesting in helping people decide modeling of these electromagnetic counterparts of Spacetime Sirens. A lot of the work, actually most of the work has been done by graduate students at Columbia that I'm sharing with my colleague here. A former graduate student, and then Phil Chang has done some of the model as well that I'm going to show you here, some application in this model. So for a few years now, I've been interested in this notion that we could detect and use the electromagnetic counterparts of gravitational wave sources, which is the thing that called Spacetime Sirens. And this led partly with this white paper that was sent to the Astroplanetary Decadal Survey with a few collaborators here. And there is basically 2 points that are made in that white paper. But there's many points, but 2 main points. One of the points that has been pushed for strongly in this area is if you can find the electromagnetic counterpart of one of these, let's say, emerging supermassive black holes at cosmical distance, you can get the luminosity distance directly from the gravitational waves, and you get the redshift from the galaxy or the electromagnetic counterpart and the galaxy associated with that counterpart. And so you can do cosmology based on the gravitational measurement of the distance. So that's interesting. I will not emphasize this so much. It's very interesting. There are some limitations that have to do with rebalancing, and so we don't know how to overcome these limitations to make this a very accurate measurement. But I won't say so much about this. It's an important motivation. But what I want to focus on is sort of the first item here. And I think that is rather exciting too. When we witness in the electromagnetic sky supernova or gamma ray bursts, we have very little understanding of the underlying central engine, the masses involved, the time scales. We have some notion, theoretical, of what's going on, but we really actually don't have any data. And so we are just witnessing sort of the outer superficial manifestation of this event in some sense. What the notion that we could detect the electromagnetic counterparts of some of these events, gravitational wave sources, is different in the sense that from the gravitational wave signal, we have a timed event with known dynamics. And knowing that, we can see how that event will manifest in the electromagnetic sky. And so it's really something a class of sources that would give us much more information. And therefore we could learn tremendously more than usually what we learn in this context of variant events. So I think that's really the motivation behind the talk, trying to at least convince you, I hope you'll be so convinced that there are these classes of events that we might be able to detect, and they might give us these like 2 windows, the electromagnetic and the gravitational, and we might learn a lot more from that dual information. So in the white paper we discussed the LIGO. There are things that can be done with LIGO sources, but I think to my mind, really the mission that will be able to enable us to do this, hopefully do this, is LISA. So my talk is entirely based on LISA sources. So it's a bit science fiction. We know now from the decadal survey that we are talking about a decade in the future at least. But there is work to be done in modeling these sources. I think to some extent there is work that can be done in preparation for the mission. So the basic setup, I won't say too much innately. To be honest, I don't follow the details of the mission concept itself. I'm mostly a user of that observatory or facility in the way I think about it. So this is this constellation of 3 satellites training the Earth on its orbit around the Sun. And I will be telling you about, and the two sort of classes that LISA will detect in gravitational waves, low frequency gravitational waves, a typical frequency of 10 to the minus 2, 10 to the minus 3 Earths, are either massive black hole coalescences in their last year of coalescence, and the typical mass involved would be a million solar mass black hole is the perfect thing at redshift 1 or 2, so you can do these measurements at cosmological distances. That's the first class of event that LISA can detect. The second class are these so-called extreme mass ratio in spirals, which are these compact objects that are fed from the galactic nucleus surrounding this massive black hole, and every now and then you get a scattering event, low angular momentum orbit, and you capture one of these compact objects, and then under the emission of gravitational radiation, it spirals in and finally coalesces with a massive black hole. And that's the second class of sources called MRIs, extreme mass ratio in spiral. And in both cases, these sources are sort of quasi-stationary or slowly decaying is more actually correct. Slowly decaying sources, shrinking sources under emission of gravitational wave. And you can observe them for a year, or maybe in some cases several years for the MRIs actually. And during that time, so you have this source on the sky, and during that time the spacecraft is going around like this, and it's modulating the gravitational wave signal on the yearly time scale. And so effectively you modulate the signal, and the way you modulate depends on the location of the source on the sky. So there is effectively a way of using LISA to localize this event on the sky. That's basically one of the interesting setup of the LISA experiment, the LISA observatory. And so as early as 98, Kurt Kepler did an estimate of the localization accuracy you might expect for LISA, for a typical massive black hole source. And he showed that using the entire signal that you get from an spiral of a massive black hole binary, you typically get to localize one of these gravitational wave sources using the entire signal to an error box on the sky of order square degree. That's a typical scale that you get, given this modulation. And given the signal-to-noise ratio, you have to do a number of things there. But the typical number that comes out is a square degree. Now, one thing that
programs a problem for that?
Sorry?
Programs a problem for that? Like binaries?
Yeah, so the foregrounds come into the signal-to-noise ratio.
Oh, it's all taken into it.
Yeah, that's taken into account. Yeah. What not being done until recently is an estimation of how this error in the sky evolves with time. And in fact, some of the work that has emerged in the last few years, that Ben's hypothesis, Scott Hughes and his student Ryan Lang, and now other people have done this with better waveforms and more detailed analysis, is that you will have this information about the localization of the sources generally weeks, maybe several weeks or months earlier before the final coalescence. So you have the time localization. You can do a calculation of the angular error on the sky as function of time prior to the merger. And it depends a bit on the type of source you have, the orientation relative to the detectors. There's a lot of time and space there. But the point is that typically, a couple of weeks, 3 weeks, sometimes a month before actually the final coalescence, you do have an error that's over the several square degrees, maybe 10 square degrees on the sky. And so you can use a large field of view telescope in principle to actually look for any signal in the electromagnetic sky that may be there. And so this has been done, this time rotation has been done for massive black hole binaries. It turned out that people have not done the extreme mass ratio in spiral case, because everybody in the community is telling me that it's obvious it's going to be even better in a notion of timing. And that's because you have a lot of signal that you build at early times for the extreme mass ratio spiral. So the notion is that you will also know way in advance where to look for a specific MRI on the sky if you see it in the LISA data stream. So that's a setup, I think, for the talk. An important motivation is that LISA will be observing these coalescing sources. We localize them before they actually coalesce, allowing us to witness what might happen in real time at the time of coalescence. And so the question I'm interested in, and I think astronomers should generally be interested in, is what are the electromagnetic counterparts we might expect from these sources? That's really, what are the plausible scenarios or likely scenarios or unlikely scenarios maybe? And this is where the picture becomes a bit complicated. It's difficult actually to answer this question. So basically the talk is organized in this way. I'll tell you about a number of scenarios that have been put forward for the massive black hole binaries, looking at a precursor electromagnetic signal prior to the coalescence. That's the work that Phil has done actually. There's been a fair amount of work on what I would call the sort of the prompt signal at coalescence, because there is interesting relativistic effect in mass loss and recoil there. I will not talk so much about this, even though there's been a lot of work that has been done on that. I think it's very interesting, and that involves numerical relativity, and I'll just have a slide on that. There's still a number of open questions there. And then I'll tell you about the afterglow. The afterglow is rather interesting. The notion there is that you see probably, if there's gas around, you expect to see an AGN turn on over a decade. At the time scale of 10 years or a decade, you might see an AGN turn on at that location. And that is pretty interesting. And then the second part of the talk, I'll tell you about this thing that I've been working on lately, which is this extreme mass ratio in spiral that involves wide dwarfs falling into massive black holes. And the tidal stripping of the warp was on its way to the horizon, basically, on its way to coalescence. And that's a paper that's just a few months old, actually. All right, so first I start with the massive black hole binaries. And again, all of this has to be looked at in a sense of toy modeling, and then trying to generate interest in this problem. So this problem of the presence of massive black holes has been looked at for decades now, and there is this well-known mass parsec problem. People have been trying to use stars to remove angular momentum and energy from the orbits of these binaries to bring them close enough that gravitational wave radiation leads to the merger of the two black holes in less than a Hubble time. That's known as the last parsec problem. There's a huge amount of literature on this. And it's a problem because once the separation between the 2 million solar mass black holes, they reach about a parsec or even 0.1 parsec, it becomes difficult to tap into these stars. Low angular momentum orbits from stars, extracting angular momentum from the orbit, because of various consideration in the rate at which that might happen in a realistic galactic nucleus. And so one of the ideas that has become popular in the last few years and decades, and partly because of, I would say, cosmological simulation of galaxy mergers. So galaxy merge, we believe they have central massive black holes. You bring the black hole together in the galactic remnant, but because you torque the gas in the process of the coalescence, you also bring probably a fair amount of gas at the center of this remnant galactic potential. So there is a notion that gas as a dissipative system might help you remove angular momentum and energy from the orbit of this black hole and therefore help you make some coalesce. Exactly how that would work is quite complicated, and there's a number of issues there. But based on that and the fact that we can take a Hubble time for these two black holes to coalesce without the help of gas, so this whole process can be read along, you might start as a plausibility guess on what sort of configuration you might get in this remnant from galaxy merger as a binary black hole. So that's what I call the general setup here, where you have a massive primary, a somewhat less massive secondary black hole, maybe so 10 million solar mass, 1 million solar mass, in orbit around each other at a parsec or a fraction of a parsec. I'm going to give you scales of like 10 to the 4 or 5 short-wave radii from the primary to the secondary. And then generically, okay, and the gas has time to cool. So removing angular momentum from gas is something that we know is not entirely easy. It's much easier to cool the gas. So starting with a cool disk configuration, gas around the binary, and why not some gas in between the two black holes? That could very well happen from an initial condition setup, or maybe some way of feeding some gas in between the two black holes, or some way for the gas from the second binary to feed an inner disk. There are various ways you could do this. So this is really plausibility. We get into toy modeling here. But quite generically, you might expect one of these cold disk configuration in the vicinity of this binary black hole. And the notion that has been put forward in literature in various forms is that the binary stalls from this interaction with stars, but the gas, by tidal interaction, is able to extract angular momentum from the binary and help coalescence on some time scale that I will leave rather unspecified for now. And then when the two black holes come close enough to each other, maybe 100 Schwarzschild radii away for the typical masses that are missing. Then gravitational wave radiation takes over, and actually you coalesce the two black holes. So that's a basic setup here. All right. So Phil has done some actual calculation of this setup, solving this one-dimensional diffusion equation, thin disk diffusion equation, the standard alpha model. And so out of this comes sort of an evolutionary sequence that is shown here. The curves I want you to focus on are this solid curve, which are the surface density of the disk as a function of separation, log of separation in a Schwarzschild radii. So you start by type interaction. So the primary is assumed to be at the center here, so dominant mass. It's not necessarily exactly correct, but it's a good first guess approximation. And then you have the secondary here. And I wonder exactly what the masses are in this model. Maybe it might be 10 million at the center and 1 million companion. Yeah, okay. So it's 10 million, 1 million. It's not really critical for the discussion here. And then this is an initial condition. We have set this up as an initial condition. By tidal interaction, the secondary opens a gap, a little bit like planets do in photoplanetary disk. Actually, exactly like planets do in photoplanetary disk, open a gap by torquing the disk around the secondary. And so the process, what happens here really is that you want to extract angular momentum from the binary, which is across here. And to do that, you need to bring a comparable amount of mass in the vicinity of the secondary as the mass of the secondary itself, so that you can deposit the angular momentum. So what happens is that you need to viscously boost up the mass you have in this binary of the circumbinary. You need to bring mass. And to do that, will take you many viscous timescales for the outer circumbinary. So that's a rather slow process. And specifically, this viscous timescale far away in the disk, the rate at which you can feed mass here is pretty long. And the timescale is longer than the viscous timescale of the inner disk here. So what happened as a result of the slow process is that the inner disk will drain quite significantly. And so naively, you might expect that you completely empty this inner disk. But in fact, the viscous evolution of this inner disk is actually slowed down because for an alpha, so assuming an alpha viscosity, as you reduce the surface density of this, you change the temperature of the disk, the viscosity changes, and you slow down actually the viscous evolution. So as the mass in the inner disk becomes very small, the viscous times become increasingly longer and longer. And what Phil found in this evolutionary sequence is this sort of a tracking solution where the viscous time of this inner disk adjusts to the actual coalescence time, essentially, for the secondary. So that's a rather interesting sort of, I would call that tracking solution. So if you follow the sequence further in time, what you find is that you keep piling up, pushing the secondary further in. You empty actually, you keep draining the inner disk. But at some point, as you approach about 100 Schwarzschild radii, something like this, gravitational wave radiation takes over. And that's a very steep dependence. The merger time due to gravitational wave radiation goes as a force power of the orbital separation. So very quickly, gravitational wave radiation takes over, and we coalesce your primary and the secondary very quickly. In fact, so fast, the timescale becomes so fast, that you freeze, from the point of view of viscous evolution, you freeze the outer disk, and you even freeze the viscous evolution of the inner disk. So suddenly the dynamics accelerates and it's entirely driven by gravitational radiation. But you keep tidally interacting. The secondary keeps tidally interacting with this second primary disk. And effectively, actually, you will probably rather efficiently extract angular momentum from the gas in this disk, so you actually tidally squeeze the disk. And what we have assumed actually in this model implicitly is that the orbits of this tidally squeezed disk remain circular. Because if you remove angular momentum, you could think of the disk becoming somewhat eccentric. We assume that the orbital energy is dissipated in the disk. So effectively, what this secondary is doing, the way you can think of it is by extracting angular momentum, and as we assume that you keep the disk circularized, what you're doing is actually binding this mass to the primary. Effectively, by gravitational radiation mediated by tidal interaction, you are binding this mass on a timescale that is set by the coalescence time due to gravitational radiation. So combining the mass, the amount of mass in the disk, which is tiny, it's about 10 to the minus 3 solar masses. So that is really puny. But the depth of the potential well and the fast time scale over which you actually squeeze this disk, you're binding a small amount of mass around a big black hole, and you do that rather fast, you can get to dissipate, to thermalize a lot of energy in this stability disk. And so what Phil found is this behavior here. So the early phases are not necessarily so interesting, but at late time, in this phase, where you actually really bind this annulus, this inner annulus, by the combination of gravitational radiation and tidal interaction, you actually, it's really easy to get that dependence. It has to do with the depth of the potential well in which you're binding the mass, and the rate at which you bind the mass, which is set by gravitational radiation. And so you get this typical T to the minus 5 force. And that should be rather universal, actually. So you get this brightening by binding this energy and dissipating orbital energy in that disk. You get that brightening of that disk on this typical power behavior that's rising like this. And it happens on a typical time scale of days before the coalescence. And then once you squeeze that disk essentially at the ISCO, inner stable circular orbit, innermost stable circular orbit of the disk, the gas gets in, the two black holes coalesce, and you've lost that inner disk. But that is an interesting scenario for a precursor Lightcurve with a typical shape that is predicted purely on the simple physical argument. Even if you have a tiny amount of mass, the time scale is so fast, and the mass of the black hole, the central black hole, is large enough that you get actually to this precursor event rising to typically maybe a tenth of Eddington in brightness, maybe days before the moon.
What of black hole masses?
Right, so again, well, I need to feel on this. I think typically it's 10 to 7, 10 to 7, 10 to 6.
And the bottom of 10 to 3.
So I'm not focusing on the numbers here so much as on 1 Eddington, which I think is more general. So we scale with the black hole mass.
So how many orbits? Is that like, is that?
Right, that's a good question. So actually, at the late times here, many of our assumptions in the model will break down because you quasi-adiabatic early on, but at the end you push tidally, and then you're merging so fast that in fact, well, from the point of view of GR, still quasi-adiabatic, but from the point of view of the disk, it's not clear that the circularization that is assumed, for instance, will remain valid. So you could imagine pushing so fast the disk into the gas that it will go through, and the regime will be different than modeled here. I think that's a scenario that can be looked at maybe the very early stages with numerical relativity, for instance. That could be an interesting project, which is something I'm talking to Louis Lander at Primary Institute. So yeah, at the very end, it's clear that this model will break down in its assumptions. So there is something else we have. Well, there is a variety of things that we have not really looked at. This is really posing the problem. And then there's a number of complications. Radiation pressure is involved. Puffing up the disk might not be clean anymore because you dump so much energy so fast at the end that you become sick. And then the tidal coupling will change. So there's a lot of things to look at more carefully in this scenario. But you have the potential for a precursor. So as I said, there's been a lot of activity in this field. I need to mention this because some people have gotten excited about this. There's been a lot of activity in the field looking at the consequence of the mass loss. When the two black holes coalesce, just further down in this evolutionary sequence, when the two black holes coalesce, they radiate a few percent of their rest mass that's gone into a gravitational wave. So any disk that is bound, like the circular binary disks that I had in the previous model, we actually feel a sudden change. From the point of view, there is a sudden change in the potential from the central mass change. And then the black hole themselves radiate linear momentum, so there is an effective recoil on the remnant black hole, so you probably bring this inner circumbinary disk with you as the black hole recoils at typically hundreds of kilometers per second. So people have done a variety of what I would call astrophysical models, various complexity. And the numerical relativists, various groups, are really gearing up to study this in more detail. So they really look at, they're looking at a variety of things. What has been done is to put electromagnetic fields around these black holes and look at what happens to them when the two black holes coalesce. Then lately, the force-free case has been done, and actually Carlos Valenzuela has been involved with this one at your postdoc here. And I think a number of numerical working groups are really gearing up to put fluids in their code to actually follow what happens to gaseous configuration or quasi-spherical configuration around these two black holes. And ultimately, I think they want to do MHD. They want actually to set up an MHD system around this massive black hole binary and see exactly what sort of phenomena you might expect from the coalescence. So it's very active, but I will not discuss that in so much detail in this talk. What I want to tell you a little bit more about is the Afterglow signature. So if you go back to my previous 2 slides or something, I really focused just on that inner title with this. Then the 2 black holes coalesce, and I'm left with this circumbinary disk here that I told you was viscously frozen around this recently merged black hole. And so from that circumbinary disk, what happens to it is that essentially it was subject to a tidal dam from the presence of the secondary, and then suddenly that dam has been removed. So all that mass will very happily viscously spread and accrete on this new primary, this new merged black hole. And so Menou and Finney have done a model of this, trying to estimate the typical time scale on which, by this simplest viscous accretion, how much it would take for actually the bulk of this mass to accrete onto the massive black hole. And at the typical separation of 100 torsion radii, the time scale they came up with is this decade. You can do that estimate. It's not too difficult. This is time scale R squared over the viscosity and given the scale. So what would happen is typically that you expect something like, and the amount of mass that's involved here and the viscous time scale that's involved leads you to believe that you will have a pretty bright Eddington or maybe super Eddington actually accretion flow developed on the decade time scales after the coalescence. So that's interesting because you know where to look, you know the masses involved, well, you know a very distinct from the original signal, and you expect actually some AGN to turn on in that part of the sky after a decade, if there was in this gas involved in the merger with this configuration. So one other thing that we wanted to reconsider in this scenario is the fact that, in fact, something that will likely happen, and that's not very easily modeled, but might be significant, is that even though it might take a decade for the bulk of the gas here on a viscous time scale to reach the central black hole, you have a steep edge here. You have a very steep edge from this tidal dam that was present early on. And so the viscous time scale is typically the gradient scale divided by the viscosity in the disk. The gradient scale here is not the radius at which this mass is located, but more the gradient scale in this steep edge. So in principle, as you have a very steep, it's like the diffusion problem in general, as you have a very steep feature that can diffuse very fast. So this was sort of accounted for in some simple way in the Menou and Finney, but we thought we wanted to reconsider that. So what I'm telling you is that, in fact, because this is so steep, in principle, there could always be a trickle of mass that could actually follow the secondary black hole as it goes towards its coalescence. And so, and that's important to define this initial condition for what happens to the gas surrounding the black hole as the mass loss, the final measure occurs, which is when most of the mass loss from the black hole happens, and which when you give this recoil impulse. So you would want to know what is the distribution of matter around the black hole to be able to model the sources accurately, understand what will happen in terms of an electromagnetic counterpart. So understanding the diffusion of this sharp edge might turn out to be important for the nature and how fast you might get a right electromagnetic counterpart in this Afterglow scenario. So what we did was very simple.
Is the velocity at that edge, small compared to the kick velocity?
It's large. So peak velocity several hundred kilometers per second. The orbital velocities at the east pole would be several tens of thousands of kilometers per second. So what you do is you truncate the disk here. The answer is typically 100 kilometers per second kick, you will truncate the disk here at the outer edge. So you will bring this with you as you report, I would think, in fast approximation, and you perturb that disk a little bit.
Yeah, a little bit.
Yes.
Question. So when you start off the black hole or the parsecs apart, if the mass of the disk is lower than the mass of the black hole, the mass of the disk is at the final separation just outside the edge. It would take multiple viscous times between the disk to extract enough angular momentum to bring black holes together. So if you start off in such a situation and you had no mass transfer across the gap, what would happen to the, I mean,
To the inner disk.
the inner disk?
So that's really,
Does it still survive?
yeah. So that's really what field. I think that's really what Field's paper is about. Actually.
But to what extent does this depend on assumptions about the mass ratio of disk to black hole binding?
Well, so Field tried various things in the paper. I don't think we have answered that question generically for the entire Canada space. And there are issues of viscosities modeling. So the various dirty properties.
So you're assuming an alpha disk.
Alpha disk, and then I should from some scattering opacity. Actually, it's a better disk because you know an alpha disk is an issue of instability. Maybe. So when you do this modeling, no radiation pressure. But what Field finds is that you do drain, most of the mass is gone. So in first approximation, the standard story, what you expect is right. You do drain the disk, but the fact is that the angular momentum is there. So there are always, it doesn't go anywhere, the angular momentum, right? So most of the mass goes in, and your residual mass that is left is all the excess angular momentum. So you have a tendency to keep a little bit of mass there, and the rate and the amount that you keep depend on the many viscous times you have.
Can angular momentum go to the binding in the inner disk?
Is where?
Well, you said the angular momentum in the inner part is there.
Right, so you can extract angular momentum flows out this way. So you can actually extract angular momentum, but for that you need gas in the proximity here. So yes, I mean there is a way for nearly emptying this disk pattern. The point is that when you model this is what Field finds is that you are able to keep what we call a fossil gas, or what you call a fossil gas, which is this is a tiny amount of mass. It's a part in a billion of the masses involved in the black hole, right? That will never screw up the signal for LISA. It's completely insignificant in many ways. But when you bind that mass quickly at the end, it can be right. That's really the point. I wouldn't claim that we have solved that problem in any way. There's a number of issues. But in the simplest alpha setup, with the sort of initial conditions we have in setup, I think this is what you might expect. It's quite possible that some tiny amount of mass could cross this gap. Actually, people see that for planets now. The setup is different, but so you could feed this disk, and that would make this precursor even brighter. So there are various ways you can strengthen that scenario.
This is probably a better application for the gap opening of the planets, because the ratio of mass of the secondary mass of the planet, and it's a bit closer to the gap planet rings.
Right, so that's true. There's various things that are very different here because the mass ratio is much more like equal mass.
No, but also the massive gap opening object is large compared to the mass of the disk in the vicinity.
Right.
This isn't true.
In the ring context, you see not getting for mass.
The ring context, the gaps are very clear.
Right. So the tidal dam here is very strong. I think that's one way of saying it. However, you just need to trickle a small amount of mass through it. So I think there's some hope there. I don't know the answer, but there's some hope that you could fit a small inner disk. Especially in 3D, for finding in 3D, there are trajectories where you can actually get some of the, at least for the planets, some of the mass in there. All right, so I'm gonna skip that. The details of what we've done here because it's not really fascinating. I was telling you that because this is a sharp edge, it can diffuse viscosity pretty fast. And so what we did is actually look at the diffusion of infinitely sharp edge. Solving this diffusion equation is linear form, where the viscosity goes only as some power of the radius, so that's even simpler. That's not as complicated even as an alpha model. But in that formulation, you can solve actually the diffusion question with a Green's function formalism. So you can start with as sharp as you want an edge and look essentially at analytical solution for how mass is able to actually follow and track this binary once the binary starts moving under the emission under radiation of Gaussian waves. And so what we find is that it's not impossible that at merger, at least this makes a case for the possibility for some trickle of mass, depending on the viscosity law in the disk, which is a complicated business, but depending on the nature of the viscosity, some trickle of mass, a very small fraction of the total mass you have here at the peak, might be able to follow this secondary black hole and be in the vicinity of the two black holes when they coalesce. And so that's interesting because it means that right away you have gas in this relativistic regime when the two black holes coalesce. So maybe that will promote also some form of electromagnetic counterpart. I will not tell you so much about it. You can calculate the luminosity of this accretion disk as you fill this cavity. It's a function of time. You get rather different answers depending on the viscosity law you assume. But and there's some issue with the models that I can get into if you want. Some problem here with the binary condition. But the basic idea is that, at least in some of these models, you don't have to wait a decade after the merger to see something happen. There is something happening even years after. Because of this fast diffusion of the age, you would expect the density to rise significantly even years after. So that's, you might not have to wait for a decade. There is issues with this. Once you release this tidal dam, the flow of mass is so large that very quickly you get a super Eddington geometry, radiation pressure dominated, advection dominated, probably thick flow. So that gets complicated to model. We don't exactly know how this flow behaves around black holes. So there is a lot of accretion physics here that we don't necessarily understand very well. We calculate the spectra assuming it's the same disk, but again, I tell you some of these assumptions break down actually in this evolutionary sequence. But really the thing I want you to get, forget all the details about what I give you about these models. What I'm trying to sell as interesting here is the fact that when Lisa tells you where to look on the sky, you might have this precursor signal. You might see a precursor. The two black holes will coalesce. People will go to the supercomputer and they will reduce the Lisa data, and they will be able to tell us, probably for good events, the masses of the two black holes, their spins. We will know the spins. They coalesce, so we will know the spin of the merged black hole. We will know the orientation of the binary orbit at least. All of this will be known. So the mass, the spin, and the orientation to a line of sight of the coalesced black hole. And around that coalesced black hole, you have an AGN turning on as mass flows in. So this is really a laboratory for accretion physics that we have never had before. And I think this is really what I'm trying to sell here as an interesting source. You might be able to study accretion physics better than we have never been able to do. Just because we have the additional gravitational information from the gravitational waves. All right. So I want to finish. So it ends at 3, right? Okay. So I want to finish with this Wadsworth Emrys. So that's more recent work. As I said, a galactic nucleus generically will be throwing compact objects at massive black holes at the center. And these are sources that can also be seen at cosmological distances with Lisa, even though not at high redshift. We're talking about maybe redshift 1 to be not much beyond. Per unit stellar mass, we produce a lot of white dwarf relative to neutron star and stellar mass black holes. So in fact, a lot of these things are a fair fraction of all these events are expected to be white dwarfs spiraling into massive black holes. Why are white dwarfs interesting? Because they have this very interesting property. It's just a bit luckier that they're dense enough. They're compact enough, they're dense enough that they can approach very close to the horizon of a black hole of about 10⁵ solar masses. But when they approach that horizon, they're tidally destroyed. So what I'm saying is that the tidal disruption radius, or the Walsh limit for the white dwarf, is just at the horizon of a 10⁵ solar mass black hole. And if actually the black hole is well, there's various things there, but in fact, what matters is really the ISCO. Where is the ISCO? When is the white dwarf falling directly into the black hole? But if you take a spinning black hole prograde orbit, you might be able to push this limiting mass to a few tens of 5 solar masses. So what I'm saying is that a subset of LISA M resources would be white dwarfs falling into relatively low mass black hole, not a million, but maybe a few tens of 5 solar masses. And at the final time of the coalescence, they will be destroyed by the tidal field of the black hole before the coalescence. So that has great potential for an electromagnetic counterpart. And the thing to remember here is that this is not the usual tidal disruption business, where we don't know where to look, when to look. We know where to look, we know where to look. LISA will have told us from a Europe observation, there is this low mass compact object in this region of the sky around the black hole of this mass and this spin. The orbit is prograde, and therefore you expect some event of interest there, if it's indeed a low mass white dwarf. So in fact, there's been a few papers on this, and I sort of got interested in this idea a couple of years ago. A group at Penn State looked at the various things like disruption condition and the signal to noise ratio of these events. And so, because these are low mass black holes for LISA, the signal to noise ratio is not so large. So it's not expected that LISA will be able to see these sources beyond maybe 200 or 300 megaparsecs. So they are cosmological, but not so cosmological. So that these are nearby M-rays. The signal to noise ratio is not so large. And they looked at this tidal disruption condition. So what I want to, and I should say because of the numerous, the large number of relatively large number of M-rays that you expect, even if 10% of all these M-rays or a few percent of all these M-rays are involved white dwarfs, there is a good chance that LISA will see several such events over its lifetime. I think that's a reasonable first guess at this. So there will be this white dwarf spiral into low mass black hole that LISA will observe. What is the phenomenology of these events? There is really two classes of events, and I will tell you about only one. So the two extreme cases are, I want to make my black hole spin maximally, A equal 1, maximal spin. I have a strong white dwarf. If I have a retrograde orbit, the ISCO is at 9 charge radii. So what happens is that I will dynamically plunge into the black hole, and on my way in this dynamical plunge, I will be tidally crushed. That might be interesting. Could you detonate a supernova? Not obvious. The tidal compression is not so strong, and you just have a dynamical time to do anything before you lose all the mass maybe in the black hole. So it's not obvious. The other extreme, the other side of this other class of events is I take again maximal spin black hole, prograde orbit, then my ISCO is essentially at the horizon. And my tidal disruption radius, by construction of the events I want to look at, is somewhat before that. So what I have is a situation where this white dwarf is radiating, well, the system is radiating gravitational waves, and my white dwarf is slowly spiraling in, and it reaches the tidal disruption radius. But it does that very slowly, so it's not really a violent tidal disruption. In fact, it is more probably accurate to call this a mass transfer event, and this is really what I want to tell you about. That we think this class of events will lead to repeated mass transfer episodes. And let me tell you why we think that this is what should happen. So I'm saying the event that I'm interested here are actually not strong tidal disruption. And that makes them, you would think that makes them less interesting, but I think that makes them more interesting for the reason I'll explain in a moment. The orbit is slowly decaying. It's generally an eccentric orbit. It's slowly decaying under the gravitational radiation. And so at some point, your white dwarf, in the very near vicinity of the black hole, feels this Warshlow. But the amount by which it feels this Warshlow is very small. And that is because the decay, the first time it feels this Warshlow is very small because the decay of the orbit is so slow. I'll give you a number in a moment. So you think of this eccentric orbit. I come at periastron, and just there at periastron, I feel my Warshlow by a tiny amount. I transfer this mass. Then I will readjust my structure. But by definition of the tidal disruption condition, when this first happened, the periastron passage time of my white dwarf is comparable to the dynamical adjustment time of the white dwarf. So to the extent that I have an eccentric enough orbit, I start mass transferring at periastron, where I feel my workflow, and my white dwarf will want to adjust by having lost mass if you want to grow bigger. But by the time it does that, it's already out of mass transfer. So naively, mass transfer from a compact object is dynamically unstable. Because you lose mass, you grow in size, so you feel you have more and more matter outfilling the workflow. But here, what happens is that the white dwarf is out of contact from mass transfer before it can really adjust its structure. So it transfers at periastron, then he adjusts his structure at apoastron, if you will, then he comes back, he transfers the liquid mass at periastron, and then he adjusts his structure again, and he comes back repeatedly. That's what the toy models that we have suggest. So it's a way, the process I'm showing you is actually a way of secularizing what is naively a dynamically unstable mass transfer. You secularize it by tapping into the eccentricity of the orbit and the fact that the step in periastron are tiny. So here is how it goes. If you use this bigger than matrix standard decay formula for the evolution of the orbit average quantities for this orbit, you find that the step in periastron from one periastron passage to the next changed by a 40 tensor 5. This goes with the mass ratio of the two objects. So as long as the eccentricity is larger than 10 to the minus 5, let's say a part in 1,000 or in 1 to 1, which is quite reasonable for this Henry vector, they tend to be eccentric, then you do tiny steps in periastron. So the first time you feel your workflow, it's a tiny amount of the mass, the atmosphere of the white dwarf, that overfills the workflow, and that is transferred, and then you don't have time to adjust, because the mass transfer episode is so short, it's comparable to your dynamical time. So you do expect this repeated mass transfer episodes. We did models of this, and I'll tell you what the model is.
Oh, maybe I'm interrupting wrong point, but what is the larger, the particle disruption radius of a AGV star, or the maximum radius of gravity wave mediated in spiral of white dwarf with the Markov massive black hole? In other words,
why do you go to an AGV star?
Well, when you're thinking an AGV star. So the question is, does the cursor?
But the AGV, I don't care about the AGV star. It's got its life, whatever. All I care is that I have this white dwarf in the galactic disk, and it's like scattered as a white dwarf.
So it's just scattered by
These are compact objects.
interactions.
I'm only inserting compact objects. Neutron stars are too. Black hole doesn't do anything electromagnetically. Neutron stars are too compact to have any finite size effect. White dwarfs are just right that you shred them just before they enter the horizon. I think that's right. So we did. I don't have much time, so I go really quickly. We did two versions of two toy models, one continuous and one discrete. Let me just tell you how it goes. We model the mass transfer while the white dwarf is its workflow along its orbit by saying that the mass of the white dwarf minus the mass that is enclosed in the workflow. So this difference is the mass outside the workflow is lost at a rate that has to do with the global sun crossing time and of the white dwarf, which is its adjustment time. And really this is more like the rate at which mass crosses at one point in this system. So but that's something that probably like sound speed is typical reasonable time. And we even did a discrete model. We don't care necessarily about exactly what happens during resolving the mass transfer, but really just saying, I assume that each periastron passage, I lose all the mass that is outside my wash surface at periastron. That's a simple discrete model. If you do that, and very important, we assume pure gravitational wave decay of the orbit, so it's bigger than matrix formula, and we assume that the white dwarf are strictly cold, and that's turned out to be important as a limitation. So by doing this, we maximize the mass loss. Really, we lose all the mass that we can lose, which is the mass outside the Roche lobe at periastron. And so we minimize the number of episodes of mass transfer. And if you do that, what we find is that you start by transferring, the part in tensor 5 makes it outside the step in periastron passage. You cube that, it's a part in the 15. So it's a tiny amount of the white dwarf that you transfer. And we do that repeatedly over many hundreds to thousands of passages. So in this simple scenario, purely cold white dwarf, purely gravitational wave decay, you're turning this, what you thought maybe was a sudden tidal disruption, into actually an episode of repeated mass transfer. And you do that, you know when that happens, because from the gravitational wave signal, you know when perihelion passage occurs. So you are transferring transiently mass onto this massive black hole in a way that is timed from the gravitational wave signal. This is a continuous model. I'll skip that. We can estimate the typical mass transfer rate when during the mass transfer phase, calculate the mass transfer rate, the rate at which we don't pass on the black hole. Very quickly in this model it becomes super Eddington. So then you can wonder what happens to this stream. You have these discrete streams of mass that will follow probably geodesics in first approximation. Will they collide with each other? That might depend on the spin and rather relativistic geometry. If they collide, you might expect them to form an accretion torus. You might, this accretion torus might produce a modulated electromagnetic emission from the shock of the subsequent streams. There's various ways you could imagine this will produce a variable electromagnetic counterpart. We have not really looked at this. It's a little bit complicated early. I put a lot of question marks. But there's a potential for variable electromagnetic counterpart at a time which corresponds to perihelion passage, which you know from gravitational waves. So what I'm telling you, and this is my last slide before my conclusion, is that these events, white dwarf spiraling into massive black holes, low mass massive black holes, have the potential of producing hours to day-long events with a possibly bright, because I'm talking about Eddington density on this massive black hole, positive periodic electromagnetic counterpart. And you know when that happens, you know where that happens on this graph. So that is rather promising from the point of view of detecting this electromagnetic counterpart. I think one issue here is that the onset of this mass transfer will depend on the atmosphere of the white dwarf. We assume it's perfectly cold. But by tidal spin-up, tidal heating, there's various complications that will come to play. The white dwarf is subject to all the tidal deformation here when it feels this broad flow. So you will heat up this outer surface. So you puff up the white dwarf. This means this might not happen just at the final coalescence. This might happen days or months earlier than you might think. So the onset of this mass transfer event is not well known if you don't know the detailed structure of the atmosphere of the white dwarf. So that's an issue for us finding these events. But I'll conclude with this. What I told you about this business of trying to find the electromagnetic counterpart of Spacetime Sirens will be really time-constrained observations in a way that we have never done before. That will require some coordination between the two communities. Gravitational wave, something like gravitational wave. There is some of this already. LSST has now, in his handbook, the handbook, they have a way of stopping their survey to look at a specific location in the sky. If Lisa feeds them, I don't know that the SST will be there when Lisa flies or whatever. But they have now accounted for the possibility that they will stop the survey to look for the possibility of a counterpart and then reconvene with the survey out of interest in this business. And so I told you about massive black hole mergers, white dwarf spirals. They really offer, I think, truly unique opportunities to really witness an AGN turn on, knowing the mass and spin of the black hole, or white dwarf being stripped, knowing the orbit, the mass of the black hole, the mass of the compact object, the spin. So you know all the geometry and the dynamics to a fair extent, and you can witness the manifestation in the electromagnetic spectrum. And I think that's good enough reason to try to model this a bit better. Thank you.